A residual network, or ResNet, is a type of neural network architecture that's designed to make it easier to train deep networks. The key idea behind ResNets is the introduction of shortcut connections, which are also known as skip connections or residual connections. Imagine you're trying to learn a new skill, like playing the guitar. You wouldn't start from scratch each time you practice. Instead, you'd build on what you already know, adding new skills little by little. ResNets work in a similar way. In a typical neural network, each layer learns some new representation of the input data. But in a ResNet, each layer learns a kind of residual representation, which is how much it needs to change the input to get closer to the correct output. These changes are usually small, which is why they're called residuals. The magic happens when these residuals are added back to the original input. This is the shortcut or skip connection. It allows the network to keep the original information through many layers, which can help it learn more complex patterns without losing the basic information. This is particularly useful in time series analysis, where the data is a sequence of measurements taken over time. The output at one time step is often a small change from the previous step. By learning these small changes, a ResNet can effectively model the time series data. In summary, ResNets are a powerful tool in deep learning, allowing models to learn complex patterns without forgetting the basic information. They do this by learning residuals, or small changes, and adding them back to the original input through shortcut connections. This code is creating a special type of neural network model called a residual network, or ResNet for short. The idea behind a ResNet is to make small adjustments to the input data as it passes through the network, rather than completely transforming it. These small adjustments are often referred to as residuals. The residual wrapper class is a custom model that wraps around another model, in this case, an LSTM model. The wrapped model is responsible for calculating the residuals. When the residual wrapper model is called with some input data, it first passes the data to the wrapped model. The wrapped model processes the data and calculates the residuals, which are the small adjustments we want to make to the input data. Then, the residual wrapper model adds these residuals back to the original input data. This is the key step that makes it a residual network. Instead of completely transforming the input data, it's making small adjustments to it. This can help the network learn more effectively, especially when dealing with sequential data like time series. The residual_LSTM is an instance of this residual wrapper class. It's wrapping around a sequential model that consists of an LSTM layer and a dense layer. The LSTM layer is designed to handle sequential data, while the dense layer calculates the residuals. The dense layer is initialized with zeros, which means the predicted residuals should start small. This makes sense because we expect the changes from one time step to the next in a time series to be small. In summary, this code is creating a residual network that learns to make small adjustments to the input data as it passes through the network. This can make it more effective at learning from sequential data like time series.